Prabha, Digital India, Educated India.
Hello student, welcome to today's lecture. In today's lecture, we will discuss how to write Hamiltonian for many electronic systems and molecules. If you remember, we have discussed the Hamiltonians of some model systems like particle in a box or harmonic oscillator, and also a real system like hydrogen atom. But in today's class, we will go beyond one electron, one nucleus example. Rather, we will go to a molecular system and write down its Hamiltonian. And while writing down this Hamiltonian, we will also see that there exists another unit like SI unit, which is called atomic unit, and how and why we need this atomic unit in quantum mechanics. That is the topic of today's discussion. Let us start by writing down the Hamiltonian of hydrogen atom. So, when I say hydrogen atom, of course, I have this picture in mind, that I have a nucleus, I have an electron. So, the Hamiltonian will have a kinetic energy term, potential energy term. The kinetic energy term will have kinetic energy of nucleus, kinetic energy of electron plus potential energy. So, every particle that we see here, every particle that we see with a certain mass will contribute one kinetic energy term towards it. Please remember, the nucleus of course has neutrons and protons, but then we are not concerned about the subatomic particles present within the nucleus. So, therefore, we will not treat them separately, we will treat nucleus as a whole, as a single particle with a certain mass of the nucleus. So, when I write down the kinetic energy operator, so we have general definition of the kinetic energy, which is minus a square divided by 2 m, where m is the mass of the particle. So, in this case nucleus, and then the Laplacian corresponding to n or the nucleus. So, this Laplacian has d square by dx square, d square by dy square, d square by dz square, where this operator is defined with respect to the coordinate of the nucleus. Similarly, for the electron's kinetic energy, we can write down where me is the mass of the electron, and this is the Laplacian corresponding to the electron's position or the electronic coordinate. Then we have the potential energy, which is a Coulombic attraction between the electron and the nucleus, and this is what we have obtained. So, while discussing this Hamiltonian, we of course separated this Hamiltonian into, since we had two particle system here, we said that okay, we can define this as what we did here is that we separated this to rewrote these two kinetic energy operators in terms of two new kinetic energies, where first one discussed about the overall translational motion of the center of mass of a fictitious particle with mass capital M, where M is mass of the nucleus plus mass of the electron. So, since we know that mass of the nucleus is much heavier than mass of the electron, so which is equivalent to mass of nucleus. And so, therefore, the first term in a way of speaking, this is simply the nuclear translational motion. The second term has mu, which is the reduced mass, defined as mn into me divided by mn plus me. So, when you see mn is so large compared to me, so this term would simply can be approximated as m of n, and I have the reduced mass is nothing but the mass of the electron. So, therefore, when I write this term, this talks about the kinetic energy corresponding to the electron, this term corresponds to the kinetic energy of the nucleus, and this term of course, we know the Coulomb interaction between the electron and the nucleus. So, this is the picture that we had for hydrogen atom. Now, let us try to increase the complexity of our problem. Suppose I have now not hydrogen atom, rather helium atom. When I have helium atom, I still have one nucleus. Of course, the charge of the nucleus, nuclear charge changed from hydrogen to helium, but I have now 2 electrons. So, electron number 1 and electron number 2. So, if I write down the Hamiltonian, which is the energy operator of this system, I must pay attention to some things. For example, in general the Hamiltonian will have a kinetic energy term plus a potential energy term. Now, kinetic energy, as I said, that each particle in my system will contribute to one kinetic energy. So, how many particles now I have? I have 3, one is nucleus, the other 2 are electron. So, I have first the nuclear kinetic energy, which is given as the Laplacian in terms of the Laplacian corresponding to the nuclear coordinate, minus now the kinetic energy of electron 1, the kinetic energy of electron 2. Please note, I have the mass of the electrons are same, and then this is the kinetic energy, and now we talk about the potential energy. When I look at this system, what kind of potential energies are there? Of course, I see that the nucleus is a nucleus will interact with each of the electrons. So, therefore, I have electron nuclear interaction, plus I see now there are more than one electron. So, therefore, there will be electron electron interaction. So, I have to worry about these terms now. So, when I write down VEN, you will see that this will be an attractive term. So, given by minus sign. So, I am just writing down here Z. So, electron nucleus. So, nucleus is here. So, let me call it nucleus as Z A, E square divided by 4 pi epsilon 0 R 1. So, R 1 is this distance minus Z A E square divided by 4 pi epsilon 0 R 2. Now, here I have these two terms, and the electron repulsion will be E square divided by 4 pi epsilon 0 R 1 2, where this is R 1 2, this is R 1, this is R 2. The R 2 is the distance between the electron and the second electron and the nucleus, R 1 is the distance between the first electron and the nucleus, R 1 2 is the distance between the 2 electrons. So, now I see I have these terms. Let us rewrite them. Okay. So, the kinetic energy of all the electrons. So, I express that in terms of a loop a summation. So, where I goes from 1 to 2. So, this accounts for these two terms, and now let us look at this term. So, I see here I can bring out this E square divided by 4 pi epsilon 0 and some Z divided by R I, where I goes from 1 to 2. So, when I equals 1, I reproduce the electron the potential energy between electron 1 and nucleus. When I is equal to 2, I reproduce the potential energy between the electron 2 and the nucleus. So, this summation sign works here, plus I have this term E square divided by 4 pi epsilon 0 1 over R 1 2. Now, what we would do is that we would see that we have in this case only 2 electrons. So, therefore, we have only one electron interaction term. Suppose we go to even more complex system. Instead of writing down the Hamiltonian for helium atom, let us say we are writing down the Hamiltonian for any atom with n number of electrons. So, when I write down for any atomic system with n number of electron, of course, I will still be left with one nucleus. So, therefore, the kinetic energy of the nucleus still remains as it is. Of course, the mass of the nucleus would keep changing. and then we have the kinetic energy of the electrons. Since I have n number of electrons, I have now this term will have n number of electron kinetic energy terms. So, here the summation goes from I equals 1 to n, and then when I look at the third term here, simple, I equals 1 to n, and I simply have still the same term R I. Now, since I have n number of electrons, I will have some changes over here, because you see when I had 2 electrons, simply 2 electrons, I had only one interaction R 1 2. So, if I introduce a third electron here, so I will have R 1 3, R 2 3. If I introduce fourth electron here, so I would see that I will have interaction with the new electron with all other previous electrons. So, therefore, there will be 6 number of terms. So, how would I do this? I have to now E squared for each term, I will have E squared divided by 4 pi epsilon 0 common. So, therefore, I keep them out. So, I have one summation I goes from 1 to n, the other summation and 1 over R I j. What would I have here, for example? If I say j equals 1 to n, so I will have a problem. Suppose let us see, if I write j equal in this summation, instead of writing here, I am just discussing what are the possible ways to write. If I write j equals 1 to n, so that means all possible values of j, I will have one problem. In fact, I will have two problems. The problem number 1 is that there will be a situation where j will become equal to I. When I is equal to j, that means I am talking about the electron's repulsion with itself. So, that is not, we do not want to have such a term there, because in that case the R becomes 0 and then the term explodes. So, I have to forbid that j should not become I. That is one problem that I must take care. The other thing, even if I consider j is not equal to I, that means I am ruling out the interaction between the electron with itself, still what I will have is that if I vary all j values from 1 to n, so I would actually end up in double counting the interaction, because interaction between 1 2 and 2 1 are same, right, because they are the same same pair of electrons. Similarly, 1 3 3 1 or 2 3 3 2, they are the same. So, therefore, I have to avoid this double counting. So, one way is I can write j goes from 1 to n, j is not equal to I, but then I am double counting. So, I must multiply this term with a half, or the other way is to write that for all values of j greater than I. So, when j is greater than I is over here, is written over here. So, if is I is 1, in that case j will be 2, 3, 4, 5, so on. So, therefore, 1, 2, 1, 3, 1, 4 kind of interactions are taken care. When I is 2, now j has to be greater than I. So, therefore, it will not consider 2, 1, rather it will consider 2, 3, 2, 4, 2, 5. So, this way I wrote down this electron-electron interaction term. So, now you see there is a problem here, is that when I look at this Hamiltonian, this looks very difficult to write. Other thing that I notice is that there are some terms which appear commonly. Let us find them out. For example, h bar, this term comes too often. The charge of the electron, this term comes too often. This 4 phi epsilon 0, this term also comes too often. And we have this mass of electron. Now, mass of nucleus comes once, but this mass of electron comes n number of times. So, you see that we have these terms which are appearing quite frequently. So, let us define a new unit system where each of these term is defined as 1, and this unit system is called as the atomic unit. We will discuss more about atomic unit in a moment's time, but what we do is that we will use this h bar as 1, E as 1, 4 pi epsilon 0 as 1, m e as 1 in this equation and see the effect. So, when I write down this one first term, so h bar square is gone. So, I have 1 over 2 m n, the Laplacian of the nucleus, minus 1 over 2 the Laplacian of electrons, because h bar is gone, mass of electron is gone. I have E square divided by 4 pi epsilon zeros are gone. So, I summation over I have Z A divided by R I plus E square and 4 pi epsilon 0 are gone in atomic unit. So, I have I equals 1 to n, j greater than I, 1 over R I j. So, I see that my Hamiltonian becomes much simpler when I use in atomic units. So, this is the Hamiltonian written down in atomic units, where h bar, E, 4 pi epsilon 0, m e are all defined as 1. So, that the Hamiltonian becomes simple. Now, we wrote down the Hamiltonian of this system, where we have for any n number any atom with any number of electrons. So, we simply have to keep changing the value of n, where I in this summation. The other thing that we should notice here is that this operator does not depend on the electron. This operator, the kinetic energy operator of electron, depends on one electron. This operator depends on one electron, because you see there is a nucleus which is there, and the electrons are moving with respect to the nucleus. So, therefore, this term depends on one electron, and these terms have dependence on 2 electrons. So, these are 2 electronic operators, these are one electronic operators, and this is a nuclear operator. This depends on the nuclear degree of freedom. Now, what we will do is that we will go to we will extend our discussion to molecular system. In case of an atomic system, of course, we saw that we have more than one electron. So, when we have more than one electron, we learned how to write those Hamiltonians. So, now what we would do is that we would go to a system where there are more than one nucleus. So, consider a some diatomic system A and B. So, it can be hydrogen molecule H2 or lithium hydride. So, where we have some A and B can be multi electronic atoms. So, atoms A has Z A nuclear charge, Z B is the nuclear charge of atom B, mass of the nucleus will be given as m A. So, mass of the nucleus is m A, mass of the nucleus B is m B, and then we have n number of electrons. So, in such a case, let us try to write down the Hamiltonian. When we write down the Hamiltonian, of course, we know that I have kinetic energy plus potential energy. When I look at the kinetic energy terms, I have kinetic energy of nucleus, or in this case nuclei, because I have more than one nucleus, and then kinetic energy of the electrons. I have n number of electrons. What kind of potential energies can I expect here? So, for example, of course, VEN, that means interaction between electron with the nucleus. We have VEE, the interaction between one electron with another electron, and the next term will come is that, which was not present before, is the interaction between the two nuclei, for example. Now, you see, when you talk about this En or EE term, we have, suppose let us define that we have n number of nuclei, capital N number of nuclei, and small n number of electrons. When I form the molecule, this n electron, suppose this is lithium and this is hydrogen, I am talking about LiH. So, lithium will have 3 electrons, hydrogen will have 1 electron, but when the molecule is formed, the molecule LiH will have 4 electrons altogether. So, once the molecule is formed, you cannot distinguish whether this electron came from hydrogen or this electron came from lithium. All electrons are practically same, they just depend on their immediate coordinate. So, therefore, we have to write this keeping in this mind when we are writing interaction between electron and nucleus or electron and electron, we have to make sure that each electron is interacting with all the nuclei present in the system. So, let us write down the kinetic energy of the nucleus. So, we have, since we have n number of nuclei, so I will try to write it in atomic units. So, so here you see that this is the kinetic energy, where h bar is in atomic unit, where I have defined h bar is 1, 4 pi epsilon, I will define 4 pi epsilon 0 is 1, mass of electron will be 1 and charge of electron will be 1. So, this is the kinetic energy operator coming from all the nuclei. So, in this case I have of course 2 nuclei. So, therefore, A will go from 1 to 2. In case I have more than 2 nuclei, I still can write this one. Please notice here m a, the mass of the nucleus, I am bringing it within the sum, because of course 2 I can keep it out, but mass of the nucleus should remain in the sum, because this mass of nucleus will keep changing when the nucleus changes. So, where for a certain value of a, I will have a certain value of m a. So, therefore, this term should be within the bracket, within the summation. Now, I come to the kinetic energy of the electron. So, the kinetic energy of electron, I have h bar square divided by 2 m e, h bar is 1, e is 1. So, therefore, I do not need to worry about mass of the electron. So, here I goes from 1 to small n and I have the Laplacian corresponding to each electron. Please notice the mass, even if I write, I can always bring this out of summation, because it does not matter which electron it is, the mass is same. Now, I come to the V E n, that means electron with the nucleus. So, these are going to be attractive interactions. So, we have to see that there are small n number of electrons and capital N number of nuclei. So, first write down I equals 1 to n. Each electron can interact with every nucleus present here. So, what I have done here is of course 4 pi epsilon 0 has been brought out, E square has been taken out. So, this should have Z into E square divided by 4 pi epsilon 0 r quantity. So, E square and 4 pi epsilon 0 are 1. So, I have removed them. Now, what I see is that I see that Z A, which is in this sum, because for each value of A I will have a nuclear charge which will keep on changing, and now I have R I A, which defines the distance between an electron I with the distance of a nucleus A. So, how many terms would I have? For each value of I will have n number of nuclear interactions. So, therefore, I will have total small n multiplied by capital N number of electron nuclear interactions here. So, this is the VEN. Now, let us look at the VEE, which is the repulsive interaction between the electrons. So, of course, this is going to be plus, I goes from 1 to small n, j greater than I, j would go up to n, but j has to be greater than I, and 1 over R I j. So, we have seen already this term, because electron interactions. So, now you see that for n number of electrons we will have these electron repulsion terms. Finally, the last term is the nuclear repulsion. Now, if I have 2 nuclei, of course, they will simply repel each other. If I have more than 2 nuclei, something similar to what we have done for the electron will also be applicable to here. So, A goes from 1 to n, followed by B greater than A goes to n, and this 1 over R A B, where R A B, this capital R A B is the distance between nucleus A and nucleus B. And mind you again, here there is an important difference. forgive me, compare this electron repulsion with nuclear repulsion. Electron repulsion has E square divided by 4 pi epsilon 0 r I j. So, E is 1 in atomic unit, 4 pi epsilon 0 is 1 in atomic unit. So, therefore, I am left with 1 over r I j. But here the nuclear repulsion would of course be Z A Z B E square divided by 4 pi epsilon 0 r A B, and E square and 4 pi epsilon 0s have been taken out, but still I have Z A and Z B because I am talking about any atom in general. So, I have now this Hamiltonian for a molecular system. Let us say I have water molecule. I have 3 nuclei and 10 electrons. So, here n equals 10 and capital N equals 3. One thing that we must appreciate here, for example, is that when I have these electrons moving around, the nuclei are much heavier than electrons. So, therefore, we can actually separate the solution of the electrons with that of the nuclei. So, what we can do is that this is the famous Born-Oppenheimer approximation, which says that you can separate the nuclear motion from that of the electron motion. When we do that, we see that while solving the electronic part of the problem, we can keep the nuclei frozen. So, therefore, the kinetic energies of the electrons nuclei will become 0 within Born-Oppenheimer approximation, and the potential energy of repulsion between the nuclear and nucleus will become a constant within Born-Oppenheimer approximation. Within Born-Oppenheimer approximation, we see we are left with these terms, which are called the electronic Hamiltonian. So, these terms together are called electronic Hamiltonian, which have 1 electron terms and 2 electron terms and a constant. Just to give you a brief idea about the atomic units, is that we have defined atomic units by defining the mass as electron mass, which is taken as 1, the charge is electron charge, the length unit. So, we have to define mass, length and time. The length unit is given by the Bohr's radius, which is 0.529 angstrom. We keep that 1 atomic unit. The unit of time is 0.24 attosecond. So, this is atomic unit of time. So, which is the time that 1s electron takes for 1 revolution, and the energy of in atomic unit is given as Hartree, which is actually 27.212 electron volt, and in this sense the energy of hydrogen atom in atomic unit will be minus 0.5 unit. So, in today's lecture we discussed about how we can write down the Hamiltonian of many electronic systems and also how we can write down Hamiltonian of a molecular system. We saw that while writing down the molecular Hamiltonians, it is very useful, or it becomes very simple if we use atomic units, where we also discussed how we have defined atomic units and the value of these different atomic units in terms of their SI units. Thank you for your attention.